Hello everyone, my name is Valeria Arciga-Valencia, and together with Fernando Elizalde Ramirez, we present our research titled Geo-Dynamic Optimization Model for Convenience Store Location. This work was developed at the School of Engineering and Science, Tecnológico de Monterrey. So here's the agenda for presentation. We will start with an introduction to the problem and our approach. Then we will cover the assumptions of the model. After that, we will present the mathematical formulation, followed by the data preprocessing methodology. Finally, we will share our results and conclusions.
Let's address the core problem. So, strategic network expansion requires rigorous analysis, and opening a store frequently leads to two primary risks. First, about low foot traffic, and second, about the cannibalization of existing sales channels. In our context, to validate our methodology, we selected as an environment the Tecnológico de Monterrey district, specifically a 1 kilometer radius around the campus. To solve this, we implemented a data science approach integrated a hybrid model. We combined the maximum covering location problem with the p-median problem. So the objective is determine optimal locations that maximize coverage while simultaneously penalizing proximity to the competition rather than just blocking it. Seen in figure 1, this is the study area of 1 kilometer around the Tec de Monterrey, and in figure 2, it is observed that after obtaining the data of the location in latitude and longitude of the existing stores and the stores that are competition are also represented on the map. To define the solution space, we established 4 assumptions. First, dynamic population. So we prioritize the flow of potential consumers rather than static census data, aiming to capture transient demand. Second, about Euclidean distance thresholds. We established a reference radius of 600 meters. Proximity below this threshold triggers cannibalization alerts. Third, about a penalty system. So the model does not strictly forbid proximity, rather it disincentivizes it through a penalty function, allowing for flexibility if the demand is high enough. And finally, about homogeneity, we assume structural and operational homogeneity among the candidate stores. For the model formulation, so we defined our sets as I for the demand zones, J for the candidate location for new stores, E and K for the sets of existing stores and competitor stores respectively. And we also defined parameters for penalties, alpha and beta, and coverage radius. We defined variables for demand of zone, distance between candidate location and existing stores and competitor stores. And finally, our primary decision variables are binary. So x sub j equals 1 if we open a store at location j, and y sub I equals 1 if demand zone I is covered. This brings us to the core of the optimization, the objective function. So our goal is the maximization of coverage adjusted by penalties. As you can see in the equation, we sum the covered demand W sub I, Y sub I, but we subtract the penalties that are P sub J1 plus P sub J2 associated with opening the store at X sub J. Subject to coverage constraints. So we are ensuring a zone is only counted if a store covers it. And second, about cannibalization constraints. So we are preventing two new stores from opening too close to each other within the penalty radius. And third, about binary constraints, that all variables must be 0 or 1. To support that objective function, we calculated specific values. For the penalties, we calculated penalties for proximity to existing stores and for competition. So we used two weights, alpha and beta. alpha is equal to, this is the penalty for being close to our own stores, so it is the highest penalty because self-cannibalization hurts our own profits directly, so we don't want to compete with ourselves. Beta is equal 1.5. This is the penalty for being close to competitors, so it is lower than alpha because even if a competitor is nearby, we can still capture shared market traffic. It is risky but not as bad as self-cannibalization, so the math prioritizes avoiding our own store first. And for the demanding scoring, for the demand W sub I, we assign weights to demand generating activities. So bus stops are the most valuable with 4 points, followed by office, schools, and finally residences. For the candidate selection and before the execution of the hybrid model, we performed a data pre-processing and feature extraction phase. So, using OpenStreetMaps data, we filtered the environment based on commercial viability and road hierarchy. The algorithm evaluates the underlying land use. If a coordinate falls on a main road, it is retained. If it falls on a restrictive residential street or a non-commercial zone, it is flagged for removal. So this ensures the model only processes viable candidates. This led us to our results. To achieve this, we executed a Python workflow combining GeoPandas and Pulp, processing geospatial data from OpenStreetMaps. So in figure 3, we observed the initial processing within a 1 kilometer radius of the Tec de Monterrey area. So here you can see how the candidate selection discriminates data. The red points represent the coordinates identified as non-viable, such as private gated communities or parks, so these are systematically discarded, and the green points are the commercial zones that passed our filter, specifically prioritizing road flow and accessibility. So after that discrimination of points and applying the function and the optimization model to our candidate points, in figure 4 we observe the solution using Euclidean metrics to minimize customer travel distance. The model solved for the strategic location of 9 new stores. So the green markers in figure 4 represent these final locations. Validating this information against our knowledge of the area, we see these points aligned with Avenue Garzazada and Avenue Junco de la Vega, so this confirms the model successfully translated spatial data into a coherent commercial strategy. So, as a conclusion of our research, first, about methodological success, so the integration of location theory with data science proved to be effective, and second, about our hybrid approach, the penalty-based model offers a superior strategic flexibility compared to rigid distance constraints. For future work, we aim to scale the study area and, more importantly, incorporate regression analysis to dynamically calculate the weights of demand nodes rather than using static scores to refine the precision of the output. Finally, I would like to thank Fernando Elizalde Ramirez for his support. Additionally, I also would like to acknowledge the Mexican Mathematical Society and Jesus Antonio Lopez Davis. Finally, feel free to connect with us on LinkedIn to continue the conversation. You can find our information on the screen. Thank you very much for your time.